Hello, I am Michiel Kouwenhoven, RF Design Manager with Linear Technology. This session discusses how to optimize the dynamic range of wideband Zero-IF receivers by addressing some of the most common issues that limit the performance of IQ demodulators, especially at very low frequencies: DC offset and second-order intermodulation products. Our new LTC5585 IQ demodulator has a greater than 530 MHz baseband bandwidth and enables demodulation of very wideband RF signals. These are encountered, for example, in digital pre-distortion applications. The unique capability of the LTC5585 to independently adjust DC offset and IM2 products in the baseband output channels using 4 control voltages enables high dynamic range in Zero-IF receivers. To begin, we will demonstrate how to adjust the IM2 in the baseband outputs. For illustration purposes, we feed two 2.14 GHz tones of equal amplitude that are separated by 1 MHz into a combiner and feed the composite signal into the RF input of the demodulator. One tone is at 2.140 GHz and the other is at 2.141 GHz. Then we use an LO input frequency at 2.130 GHz, that is 10 MHz apart. The two tones are predictably demodulated at 10 MHz and 11 MHz, as shown in this spectrum analyzer plot. As the second-order intermodulation products, down-converted to the difference frequency of the two input tones, fall in-band at 1 MHz, as shown in this measurement plot. If we can reduce this IM2 spur, the input IP2 performance will improve. The LTC5585 has a built-in input IP2 optimization circuit which allows us to improve the performance parameter at both the I and Q outputs. The adjustment is made with 2 independent analog DC voltages, for example, implemented by 2 trim potentiometers, as shown in this circuit. By adjusting the voltage, we can tune the IM2 spurs to drop as much as 20 dB to -81.37 dBc below the main tones. That is almost at the noise floor of the receiver. We can also demonstrate this in real time on the spectrum analyzer. Observe the IM2 tone at the left of the screen. When I change the voltage on the IP2 adjustment input, the magnitude of this tone is clearly changing. Once optimized, the performance should hold up fairly well over temperature, as shown in the graph on the left. If we calibrate the input IP2 at room temperature, that is the green colored curve for both I and Q outputs, it worst case degrades only to about 60 dBm over the temperature extremes, from -40 degrees C to +105 degrees C. The plot on the right-hand side shows the variation of the input IP2 versus the RF tone spacing, before and after calibration at 1 MHz spacing. In the vicinity of 1 MHz spacing, calibration clearly improves the input IP2, while the improvement gradually reduces when the spacing moves farther away from the calibration point. To achieve input IP2 improvement for wideband input signals, we therefore advise to calibrate the input IP2 at a spacing of about half the signal bandwidth. Thus for a 100 MHz wide signal, we recommend to calibrate at 50 MHz tone spacing. Using a similar adjustment technique, we can also zero out the DC offset in the I and Q outputs. The LTC5585 typically has 6 mV of output DC offset, while the built-in offset adjustment range is about ±20 mV. This leaves enough room to null other offsets in the signal chain between demodulator and analog to digital converter, resulting in a higher receiver dynamic range. Besides the LTC5585, A lower frequency version, the LTC5584, is also available that has the same optimization features. Below 450 MHz, the LTC5584's input IP3 and input IP2 performance are even more impressive. Regardless of your application frequency, using these products you can now build a truly high-performance Zero-IF receiver with outstanding linearity, no DC offset and wide bandwidth. For more information, please visit linear.com. Thanks for watching.